How do you calculate view factors for intricate geometries? Imagine trying to figure out how much radiation one complex shape can see of another. That's exactly what view factors help us understand in heat transfer and design. They tell us what fraction of radiation leaving one surface reaches another directly. For simple shapes like rectangles or cylinders, we can use formulas. But when the shapes get complicated, things get tricky. That's when we need to turn to numerical methods and computer calculations. First, we need to understand what a view factor actually is. It's defined by a double integral over the two surfaces involved. This integral considers how the surfaces are positioned, their orientation, the distance between them, and whether they can see each other. The angles between the surface normals and the line connecting small areas matter a lot. For complex shapes, this integral becomes very hard to solve directly because of the irregular geometry and possible obstructions. To handle this, we break down the surfaces into many small pieces or facets. Think of it like dividing a complicated shape into tiny tiles. Each tile acts as a small, simple surface. Instead of trying to evaluate the integral over the entire shape at once, we sum up the contributions between all pairs of these tiny facets. This makes the problem manageable and allows us to use computers to do the heavy lifting. There are several ways to do this. One common method is ray casting. Imagine shooting many rays from one facet toward others. If a ray hits the target surface without hitting anything else in between, we count that as a successful connection. By doing this many times, we estimate what fraction of radiation from one surface reaches the other. This method works well for complex shapes and can be optimized for speed. Another approach is Monte Carlo simulation. Here, we randomly cast rays from the source surface and see how many reach the target. It's like tossing a lot of tiny balls and seeing how many land on the other surface. This method is flexible but can take longer because it relies on many random samples to get accurate results. Finite element or finite volume methods are also popular. They involve creating a mesh of small elements over the entire geometry. Then, we calculate the view factors between all pairs of these elements. This results in a matrix that helps us understand the energy exchange in the system. It's especially useful when dealing with complex, irregular shapes. Sometimes, geometric tricks are used for specific cases. For example, if surfaces are curved or partially blocked, geometric constructions can simplify the calculations. But these are limited to certain shapes and situations. Obstructions and shadowing are important considerations. If one surface blocks the line of sight to another, the view factor between them drops to 0. To account for this, we check if the line between two facets is clear. If it's blocked by another part of the geometry, we exclude that contribution from our calculations. Because these calculations can be complicated and time-consuming, specialized software tools are often used. Many finite element analysis programs include modules that automatically handle surface discretization, visibility checks, and numerical integration. This automation saves a lot of time and reduces errors. In real-world applications, accurate view factor calculations are vital. They help us design efficient furnaces, electronic cooling systems, solar collectors, and even analyze building heat transfer. Knowing exactly how much radiation is exchanged between complex surfaces allows engineers to optimize performance and energy efficiency. So, in summary, calculating view factors for intricate geometries involves breaking surfaces into tiny elements, then using numerical methods like ray casting, Monte Carlo simulations, or finite element techniques. These approaches help us understand how radiation moves between complex shapes, which is essential for designing better thermal systems.